So thank you for joining us on another Cambridge Carbon Footprint Open Eco Homes online tour. Our host today will be Olly Cooper, architect and passive house consultant working with Matt's Fordham. He's been really motivated by his desire to create an environmentally and sustainable home, which is transformed his 1920s home in Garlick Row to be fit for the 21st century. So he's going to show us first a bit how his motivations and some of the results of that. Then we're going to have a short break, maybe a few questions, and then he's going to present a bit about some of the details and things that he's actually done in the house. And then hopefully we'll have a bit more time for some questions after that. Okay.
Brilliant. Oops. Okay, I'll get started now. Thanks everyone for joining us. Yeah, I'm really pleased to be here and able to present this project, which is my own home. Not often you get to present your own home as an architect, so yeah, I'm looking forward to it. So I'll just crack straight on. First thing I wanted to say is there is a PDF case study of this house on the Open Eco Homes website, and it contains some of the costs associated with the project, so maybe of use to have a look at that. Yeah, and if there's not questions there, you'll get my email address at the end of the talk, so you can ask me about costs further if you have any particular questions about that. As Fran said, this is the plan. We're going to talk about motivation, retrofit principles, targets, the results. I'll have a short break for questions, and then we'll get into the detail on airtightness, ventilation, floor insulation, wall insulation, roof insulation, air source heat pumps, etc., and further questions at the end. So this is the house. It was built in the 1920s. It's a 3-bedroom semi-detached house, and it's got solid brick walls. And on the left, that's what it looked like before, the existing metal frame windows. And this is what it looks like now with a small side extension. You can see the heat pump in the front there, and you can see the photovoltaics on the roof. So why retrofit? What were my motivations? Well, one of them was comfort. It was an extremely cold house, incredibly drafty, incredibly hard to heat. And this photo was taken with one of Cambridge Carbon Footprint's thermal imaging cameras. So it gives you an example of all the air leakage coming around the door from the kitchen into the cold garage. And you can see the air leakage in blue going across the floor and cooling down the concrete floor. And in general, it was just a very uncomfortable place to be during winter. So this slide is just to try and convey the kind of well-being benefits and comfort benefits and delight benefits, hopefully, from the retrofit. So that's what the staircase looked like before on the left, and then that's me painting it recently on the right. Then I'd say a primary motivator for me was in tackling the climate crisis. So this slide is just to remind us sort of where we are with that, and it's a bit of a shame that I have to say this this week with what Rishi Sunak seems to be doing, but basically we're not going fast enough. This chart is from the Committee on Climate Change, the committee to Parliament, and it shows that essentially if we strip out electricity supply, which has been decarbonising very quickly, or fairly quickly, on track, I should say, really. If we strip out that, and if we strip out aviation and shipping, which have been varying very wildly since COVID, then what we've achieved is about 1.2% emissions reduction in the UK per year. And what we need to achieve to stay on track for our 2030 climate budget and legal target is 4.4% a year. So we basically need a 4-fold speed increase, not relaxation, as some may say. And this shows for buildings where we are. This again is from the Committee on Climate Change. And the red ones indicate where we're off track significantly, and the yellow ones where we're slightly off track, and the green ones are where we're on track. So starting with the green, we have the electricity price to gas price is currently on track. They're trying to make sure that the electricity price stays low in comparison to gas, which is a good thing for people who want to switch to heat pumps. And they're also doing okay in government buildings, but everywhere else, either we don't have the data to say or we're off track. And so that includes things like number of trained heat pump installers, heat pump installations, which are significantly behind where we need to be, households receiving energy efficiency measures, and the cost of those measures. So yeah, even the one that says slightly off track there, which is a very important metric for overall heat demand of buildings in the UK. If you look at the line, it's basically flatlining sideways when it's supposed to be curving upwards. So it's quite concerning where we are at the moment. And so we really need to push for, a faster and harder approach, I think, in terms of our building stock. So as Fran mentioned, I'm a passive house consultant and an architect. And so this retrofit was done in accordance with passive house principles. And what that means is, starting on the bottom left here, we have 5 principles of passive house. So really good levels of thermal insulation in the building, the opaque elements of the building. And that's combined with designing out thermal bridges, so weak spots in the thermal envelope, where if we just slap a load of insulation on without thinking how it all joins up, then we run into issues. And we make the building extremely airtight, and that saves a lot of energy. And we combine that with a very efficient ventilation system that recovers heat from the outgoing air, so that we basically have very low heat loss in winter. And we have triple glazed windows, which have 2 benefits. They both reduce the amount of heat lost to the outside world in winter, and they also improve the thermal comfort in the building by being warmer. The inside pane of a triple glazed window is warmer. So the radiant temperature that your body experiences is actually warmer than just the air temperature, because you experience the radiant temperature of the internal pane of glass. So they have kind of a double benefit there. So now I'm going to just touch on the targets for this project. So the primary target, I would say, was getting off gas, no fossil fuels on site. So this is a picture of the gas pipe that was capped off, which is very pleasing to see. And that seems to me to be the fundamental aim for a sort of decarbonisation retrofit. And so that was achieved. And then this chart shows some of the ideas about where we might need to be sort of if we try to put carbon emissions into a kind of context that we can understand per person. So this book, Living the 1.5 Degree Lifestyle, references this report, which suggests that if we all converge on 2.5 tons of lifestyle emissions by 2030, then that would be on track for a 1.5 degree overall increase in temperature. And so you can see on the left here some different countries in that report, and you can see that Brazil and India are close to where that target needs to be, and their emissions from housing per person are around 400 or 500 kilograms per person. So I thought I'd use that as a reference point. In the UK, we're currently about up here by my estimate. So moving on to the performance of the building and how it's actually done so far. Before the retrofit, it was extremely energy intensive. We were using lots and lots of gas. That's the blue bar on the left here, and quite a lot of electricity. And afterwards, we're just using electricity. And although that's gone up by a little, it's not by that much. In terms of the costs, before we were spending about £2,200 or so per year. That would have been what we would have spent if we were using today's prices. Obviously, back in 2021, prices would be a lot less. But at today's prices, we've made a saving of about 54% or just over £1,000. And that's combined with a huge increase in comfort. So these energy bills were delivering kind of an average temperature in the house of, I think, my modeling suggests it would have been around 16 degrees Celsius on average. So getting really cold when the heating is off at night and in the middle of the day, and only being heated just in the morning and the evening. And now it stays at a nice steady temperature all the time through the winter. And so this is the carbon emissions performance. So at today's electrical grid, it's gone from about 3.6 tons down to a little under a ton of carbon emissions per year from the on operational energy. And by 2030, because the grid is decarbonizing, that will reduce further to perhaps 160 kilograms. In terms of the way we measure buildings in the UK, what we usually do is we measure them per square meter of floor area. So the metric you see here is the total energy used by a building divided by its floor area. And you can see that, typically our buildings use around 200 kilowatt hours per meter squared of floor area per year. And new buildings use quite a lot less than that. If they're built really to how the building regs say, they should use just over 50 kilowatt hours per meter squared per year. Unfortunately, that's sort of a modeled metric, not actual performance for new builds. And you can see here on the right, the blue bars are where we were before. So it was a little worse than average. And now afterwards, we're in line with new buildings, possibly approaching kind of passive house new build type standards, although we're a little way to go before we quite get to that. This is based on sort of average use. Maybe we're a bit under, but that's probably because the occupancy is quite low, etc. And so I don't have a breakdown of what the energy use was used for before the project, but I can model that. That's what a passive house consultant does. We model energy performance of buildings and help designers to improve them. And this is my modeled breakdown of what that energy use would have looked like. So you can see the red bars, the vast majority would have been on heating. And the next biggest thing would have been hot water, and then everything else roughly similar. And that's why we tend to focus massively on the heating performance of buildings in this country, because that's dominant energy use. And this is another chart. Sorry, my first part of my presentation is pretty charts heavy. I promise the second part has a few more photos. So this is the modeling done in what's called passive house planning package to show where the heat loss from the building exists. So on the left, we have the existing house. And so on the far left here, we have all the losses throughout the heating season. And on the right, that's balanced out by some gains. So starting at the top here, we've got the heat loss through the walls, the light blue here, and then the heat loss through the roof, heat loss through the floor, heat loss through the windows. And this green part is the heat loss from ventilation, which in the case of the existing house was all just infiltration, uncontrolled through leaky windows, and maybe a small amount from the extractor fan in the bathroom, but predominantly it's just basically the air leaking out the house, all through both the windows and the floor and the roof and all kinds of places. And so over this heating season, that's balanced out by a bit of solar gain that you get for free through the windows, which is the yellow part here. Some internal heat gains, which you get because you have people in your building and you have appliances, and that all contributes to heat in the building. And then the red part, this shows what the heating system was having to make up. And this is all per square meter of floor area of the building, so that we can compare different buildings of different sizes. And over here we have where we've got to now. This is again just modeling, not actual measurements. And so we've cut the heat loss through the walls by insulating the front of the house with internal wall insulation. We've cut the heat loss through the roof, which was already insulated with 100 mil of mineral wool insulation, down to a tiny amount because we've got 360 mil of mineral wool insulation in the roof. We've cut the heat loss through the floor because we've insulated the suspended timber floor between the joists of the floor and below those joists. We've got triple glazing at the front of the house, which has cut the heat loss a fair bit from windows. And we've massively reduced the heat loss from ventilation by making the house extremely airtight and putting in one of these mechanical ventilation systems which recovers heat. And so that's where we are now. And then phase 2 would be to insulate the back and the side of the house. So that's gets the heat loss from the walls right down, and also to put triple glazing in at the back of the house as well. And that would get us down to a heating performance that's approaching the Passive House retrofit standards, but not quite there. The chart I just showed you was based on the fact that it was very cold in the winter in the existing house. If you actually just said we wanted to heat everything to 20 degrees Celsius, which is what we assume in these cases, then the reduction in performance is even greater. But of course, that wasn't what we were doing. We were heating the house intermittently beforehand. And so this is the plan of the house. And you can see in red here everything that we demolished. It was a pretty extensive refurbishment. We made the whole house open plan. So that involved putting in steel beams and completely opening up the downstairs. We reorganized the house, and I'll show you some photos of this very awkward staircase that existed when I purchased the house. And we made a huge effort to try and improve that, because I was struggling to get down the stair. I'll show you in a moment, actually. I've got a photo of it. So yeah, it was pretty extensive demolition. This is the plan as it is now, the proposed plan. So you now come into a more generous hall without a staircase directly on your right, and the staircase goes up and round in a U shape over here. And what that did is it meant that there's a much better space for a bathroom on the upstairs, which was very compromised by the stair in the existing house. And then we've got an open plan kitchen facing the dining room and living space. And yeah, we added a small shower room to the side, and then this is the plant room, which contains the mechanical ventilation system and the cylinder for the heat pump. And you'll see that this is still quite a compact form, and that helps with the heat loss. So we've kind of insulated the side of the house by virtue of building an extension against it, as opposed to extending into the garden and it becoming a very long, elongated form, which would lose more heat. So this is what I was talking about. I'm 6'4", and this staircase was not adequate for me to get down. I sort of had to pirouette to get down the stair beforehand, and this was the bathroom. You can see that there's a sort of sloped bit of floor under the sink, and so it was just totally ridiculous, really. And I bought the house really wanting to retrofit it, so I guess I spotted stuff that I saw I could improve. And so this is an improved stair now, and you can see I made sure that I could stand up on the stair. So these are just some photos of the project to finish off this first part of the talk. So on the left, you see the existing stair, and then this in the middle was partway through the build with the new stair in place. And on the right here, this is how it looks now. I have to say it's not quite finished. There's still quite a few little things to do, but once the house is habitable, it becomes a bit less. There's a bit less motivation to keep going. This was the kitchen beforehand with the gas hob, and this is what it looks like now with the induction hob, electric induction hob. And this was the back room, which is now the dining room beforehand. And this was it partway through with the steel beam going in to open up the plan. And here it is a bit further progressed with us clearing out the floor, ready for the floor insulation. And a bit further on, this is the internal wood fiber insulation going on at the front, plastering going on, and getting towards finished. And this is what it looks like now. Okay, that's the first part done. We're going to have a quick break, I think.
Yeah, if anyone's got any questions to sort of clarification things on that first part, you can either put the message on the chat or just take yourself off mute or put your hand up.
I had a little question for you, Olly. By comparison with other types of houses that you showed, like bungalows, freestanding detached houses, semi-detached like yours, and say a flat in a block of flats, where roughly does your house stand in relation to the number of kilowatt hours per square meter used in a year? Is a little house like yours, which is semi-detached, is that in the middle of the range, or is it better than average? You know, what are the best houses to look out for if you were buying a house? Where would you be best to spend your money on the kind of shape and form of a house? Sorry, long question. But...
Yeah, I think I can have a go answering that. So you'll see here, these are what the Letty, which is a good organization that do a lot of research into retrofit and energy performance of buildings. This is what they've modeled different buildings in the UK will perform at. And I'm not quite sure why flats don't perform so much better. There may be a reason that, you know, the housing stock must be skewed in one direction or the other, because this is averages for the whole of the UK. But you would expect that flats would perform a lot better. And in general, if you are looking to live in an energy efficient building and you want to move, then buying a flat is not a bad thing to do, just because you've got lots less heat loss in a flat for the total floor area that you're going to use. So yeah, I'm not entirely sure what's behind these figures, but that's where they placed it. You would expect the bungalow to perform quite a lot worse, but it's possible that bungalows generally are more modern than, say, a lot of terraces, which are probably more likely Victorian in this case. So the house performed a little worse than all of those buildings, worse on average previously, and now it performs considerably better than the average house per square meter, and actually better than a new build house built today. Hopefully that's clear. Cool. Yep.
Thanks, Ollie. Just question is, what thickness of wood fibre internal insulation? What thickness on the walls that you will ultimately insulate externally? Will you insulate any walls, both internally and externally?
So no walls will be both internally and externally insulated. The internal wall insulation that went on in this case was 100 millimeters of wood fibre. And I'll discuss that in a bit more detail going forwards. Externally, I think that modelled was 120 millimeters of wood fibre, or something of that order, yeah, for that phase 2 part. That's what I'd planned to do, something like that. Yep.
Okay, thank you. Brilliant. Thank you. Ollie, if you want to carry on.
Cool, excellent. Okay, so I'm going to talk through some of the specific technologies that we use. So I'm going to start with the air tightness measures and the mechanical ventilation with heat recovery. So just to remind you that this was basically getting this number 62 kilowatt hours per square meter per annum down to around 8, and it's a key part of the strategy. So the first thing is, how do I know that it was 62? And the answer is that's a model number based on some assumptions about how infiltration works in a building, but it is modeled based on a test, and the test was it's called a blower door test. And so you get someone to come along and put a big fan in the door, and then they pressurize the building, and the air, the house gets pressurized up to 50 pascals of pressure difference between the inside and the outside, and then the air is trying to escape through all the cracks and leaks in the house, and it does so. And then you measure the airflow through the fan, and that tells you how much air is leaving the house, and then you can work out the how much air leakage the house has from that. So use that number at this standard pressure difference. You also depressurize the house and test it that way, and then you apply that to a sort of more normal pressure difference that would be experienced by the house on a typical winter day through you know, the blowing of the wind and the temperature difference between the inside and the outside of the house, etc. And so the first thing to do is to design your airtight line around the building. So that's this red line on this section here. And so that you know exactly where you're trying to provide the airtightness. And you only ever have one airtight line that you stick to, just like if you had, say, a leaky bucket inside another leaky bucket, it would all still leak. What you want is a single solid bucket, a good bucket, and that's what you're aiming for with airtightness. And so the strategy in this house was to put plywood deck on the floor, and that's this white here. It was actually painted with a airtight paint just for extra belt and braces, and it was all the joints were taped with a special airtight paint tape. And then the walls were plastered with a lime plaster. A thick, wet coat of plaster is a good thing for airtightness, and that was all of the windows are taped to that layer of plaster. And the new windows are very airtight. They're what's called air permeability class 4. Basically, they've got, in this case, double seals to make sure that they're really airtight. And then little details like the floor joists taped around those, so plastered right down and through past the joists, because usually the zone between the joists in the first floor of a house is never going to be plastered, so we plastered that and then taped around the joists. In the ceiling, we used a special airtight chipboard, which sits here above the ceiling joists, and that allows you to run cables and services in the ceiling without having to penetrate that line, which is good because every penetration in the airtight line is another thing you have to seal up. And we developed a detail for the eaves, which allowed you to bring the airtight line round from the plastered wall and up onto that chipboard. So it involved using a piece of membrane and some bits of wood knock-ins between the ceiling joists, and those allowed you to tape around each ceiling joist up and over into onto the deck above, which was quite fiddly, but helped by bringing that further away from the eaves so that you could get your hands around it to do the taping. And so here the details, sorry if it's not that clear on the screen, but you can see that the red line is continuous and every bit of tape is shown so that it's very clear where you're going to put the airtight line. And it also meant that the insulation could wrap right down into the eaves and form a continuous thermal line with the wall so that there's not a cold bridge there. So yeah, where we did need to penetrate that deck, we used special grommets to allow the cables, for example, for the photovoltaics, to go up into the loft. And the result was an 87% reduction in air leakage across the whole building. So pre-retrofit, we had a air tightness of 11.6 air changes per hour at that 50 Pascal pressure difference. So the whole volume of the building changing 11.6 times in an hour according to, at that pressure difference. And now we've got that down to 1.5. And the target after phase 2, which would be the passive house retrofit standard, which is called Retrofit, would be to get that down to 1. And you can see these grey bars show you what a new building would look like. So again, for building regulations, that's not a particularly difficult thing to achieve in a new building. So it's something that the building regs looking to improve in the coming years, but it's not a very onerous standard at the moment. And so we provided that air tightness, and then we need to make sure that we provide good ventilation to the house. Previously, the ventilation would have been fairly intermittent based on just whether the wind is blowing and etc. Now we have dedicated continuous ventilation to every room, and that's provided by this series of ducts, which both extract from the wet rooms and supply to the habitable rooms in the house. And the extracted air is all brought back to a unit in the garage. and that's expelled out into the garden. And as it's expelled, it's passed over a heat exchanger for the fresh air coming in. And so it picks up 90% of the heat that's in the air going out, gets recovered and put back into those supply ducts. And so this is me laying out the ventilation system on the floor, ready to install it. I installed it myself over, I think it was about 5 weekends. It was quite slow because I'd never done anything like this before, although it was a bit like a massive Meccano set and I really enjoyed doing it. This is in the kitchen ceiling where I was attaching the ducts to the underside of the floor. So all the crossover of the ducts and the largest attenuators, you can just see one of the attenuators on the right here, which avoid the crosstalk between rooms and also avoid you hearing the fan. So it's incredibly quiet when the system is on. You don't actually hear the fan from the unit because of these attenuators. They're all housed in this bit above the ceiling of the kitchen, this sort of blue bit on the plan here. And you could just see from this photo that the ceiling level is dropped to accommodate that. So you can get all of that stuff in and avoid having to cut joists, etc. by having that drop ceiling. We did have to cut just one joist for this pipe, this duct, sorry, that runs to serve the living room. And other than that, we didn't have to do much altering of the structure to fit this in. We have a riser up through this third bedroom, so it's a small compromise in terms of floor area, and then we rise into the loft and distribute within the loft under the insulation there in the loft. So this is the unit, and the supply and the exhausts ducts, and on the right here are the that's the supply vent and the extract vent into the garden, and in the middle this is a sped up video of me Googling. I don't know what I was Googling, but me fitting some of the duct work using a jigsaw to cut the ducts, and then fitting it in place in the garage. And this is the plant room, which I showed on plan at the start. The unit, the MVHR unit itself has filters in it, which need to be hoovered every 6 months. Well, hoovered after first 6 months and replaced after a year. So all of that particulate matter hasn't ended up either in the house or in the heat exchanger of the unit itself, so it's protected from that. And this is the control for the ventilation, and just to show you, it works both to recover heat in the winter, but also in this case here, you can see that the outdoor temperature is at 28 degrees and the indoor temperature is at 25 degrees-ish. And so it's actually working in reverse to reject the heat coming in on the very hot day in summer. So it does both recover heat and cool. And during the summer on a, say, fairly warm day, where it's, say, 23 degrees outside and 26 degrees inside, but you want it to be a bit cooler than that, it will open a bypass automatically, so it won't be recovering the heat that you don't actually want. So it will do that for you because it has temperature sensors in the inlet and the exhaust. So yeah, in terms of pros and cons of this system, I'd say the air quality, supplying every room continuously, is a real pro. It's comfortable because it supplies at a very low speed. It doesn't produce any drafts, and it provides significant energy savings. In terms of cons, obviously it was pretty invasive fitting those ducts, and you do require space to fit the unit. I should say that the one that's shown here was actually much bigger than potentially needed to be, because of just the fact that the people who supplied it at Green Building Store had one that had suffered some damage in their warehouse, so they gave it to me for cheap. It didn't really need to be this big one for this house. It's not a huge house, and it is more expensive than demand controlled extract ventilation or other forms of extract ventilation. Okay, I think I better crack on. We'll move on to floor insulation. So here we're looking at the brown element of the chart. So we're going from initially 55 kilowatt hours per square meter of floor space to, I think that's 8. And we did that by insulating between and below the floor joists. And so the floor joists are just 100 mil deep, as is common in houses like this. And underneath you've got a ventilated zone, which was previously ventilated with air bricks. We added a telescopic vent so that the ventilation was preserved, and we actually added a couple of air bricks to make sure it was well ventilated under here. And then we put in some hangers, which are formed of bits of plywood and a batten fixed to the side of the joists. That's just to extend the zone available for the insulation, just to make it a bit deeper so we can get more in. And then we put in insulation, or put in a breather membrane, which is fixed up from below in the gap below that's preserved 150 millimeters minimum for building regs. There's a gap there that remains ventilated, and then we put the insulation on top of the breather membrane. We taped all around the breather membrane just to stop any wind washing from that ventilated zone affecting the performance of the insulation, and then put in the insulation itself. And on top of that, we put in that plywood deck that you saw earlier for the airtightness. And this is showing taping of that deck to the wall where the plaster was continued right down to attach to that taping. So hopefully that's not going too fast, but these are little bits of technical info and just how we did it, hopefully useful. I'll keep going. We're going to move on to internal wall insulation. So in terms of the internal wall insulation, we started with a huge heat loss from walls, as you can see, and we've ended up with still it dominating the heat loss in this cyan colored part of the chart, but it's considerably reduced and we're ready for phase 2. So this is the front of the house. Here there's a lime plaster going on, sometimes referred to as a parge coat. And that does a couple of things. It provides the air tightness that I mentioned earlier. It also levels up the brickwork so that the insulation can sit flat against it. And you can see it's being taped onto the window here. And that's a bit of a closer detail of that tape. It's a special fuzzy back tape, which allows you to plaster right onto it, and it keys into the plaster well. And so then the wood fiber goes on top of that, and it overlaps with the window frames to try to reduce the thermal bridging. A weak spot usually is a point where heat can pass through the window frame or adjacent to the window frame into the wall. So we try to overlap the insulation with the window frame as much as possible. And then it gets covered in a lime plaster, which I'll show you in a second. So the building is very airtight, and this plaster provides airtightness, but it's quite important to realize that that doesn't mean it's not breathable, as is often the word that is used. I think a better word is moisture permeable. The whole build-up is still moisture permeable, and one does need to be a little conscious of moisture risks when it comes to internal wall insulation. In this case, I'm using wood fiber, which is a hygroscopic material, which can be used to minimize that risk. But yeah, certainly some of the methods to reduce that risk are to limit the thickness of insulation and to use hygroscopic materials, and to basically making it airtight actually reduces the risk, because what you don't want is cracks and crevices to allow moisture from the warm and moist interior right into the cold brickwork of the building. Essentially, the internal wall insulation is cooling down the brickwork, and that's why people say, there is an increased moisture risk associated with internal wall insulation. Wherever possible, it's often a lot simpler to do external wall insulation. In this case, I decided not to, because I wanted to preserve the brick appearance of the outside of the house. And this is just an example where, because we were replacing the floor on one half of the house, because of moving the stair and the fact that it actually suffered subsidence, so it was easiest just to replace it, because this whole house has actually been underpinned, which means it's been propped up on new foundations under the existing. this is a case where we actually put in a new floor, and so that allowed us to have the avoid the joist penetrating into the cold brickwork and avoid that moisture risk to the joist ends, and also continue the airtight layer up and past the floor by putting on that plaster coat before we did this work. And so that, this major retrofit approach did allow us some flexibilities that wouldn't normally be available to people by doing that sort of thing. And that's the finished result, which is a lime sort of plastered finish, which is going to be left exposed with a clear glaze. Okay, moving on to roof insulation. So now we're looking at this darker blue part of the graph. It was already quite a bit less than other areas. It had 100 mil of mineral wool insulation already there, as I mentioned earlier, and we got it right down to a small amount. I think it's 4 kilowatt hours per square meter per annum of heat loss. So in this case, the roof was reaching the end of its life, the roof covering itself. The slates were weathering very thin, cracked in places, and there was no membrane underneath. So in fact, we needed to re-roof. Inside the roof, you can see here, I'm removing some of the old mineral wool insulation. You can see the lath and plaster ceiling below. And then this was the chipboard deck that I mentioned earlier, all taped up with Airtightness tape that went in first. You can also see some of the ventilation ductwork that was distributing to each of the bedrooms, which, because of you would ideally keep that below that chipboard inside the airtight layer of the house, but in retrofit you often have to make compromises, and this was one. So we had to tape up around each of these ducts, but they do remain under the insulation layer, which you can see going in here. So we've got 360 mil of mineral wool insulation that went in 4 layers, all carefully packed in and cut neatly around all the obstructions to avoid any kind of thermal bypass that could occur from gaps in the insulation. And the layers were staggered so that the joints don't line up, which is a good idea when you're trying to really make sure that you get the best thermal performance. And you can just see here there's a little sort of stub wall of timber, and that was to allow us to put in this storage deck, which finishes off the attic space. So that spans from the party wall, the chimneys, across to that stub wall, and therefore doesn't require any of those kind of supports that you might get in a loft deck installation. And that avoids the thermal bridging from those, and also it just allows you to fit the insulation a lot easier and more neatly. And so here is the re-roofing going on with some new battens. And at the rear of the house, we took the opportunity to extend the roof, and that gives us an eaves, which has been insulated right down into the soffit of the eaves, all ready for someone to come along later and just put up some external wall insulation and maybe put in some new windows and bring them forwards to line with that insulation all in one go, and not have to think about the roof again, because it will all join up neatly. So that was one bit of sequencing work that we did to help ourselves in the future. And this is the photovoltaics, which are inline photovoltaics made by or designed by a local company called Viridian, installed by another local roofer called Bowler Roofing, who do this kind of solar work. And I just like the look of the inline ones and think they look quite cool in black, and they don't produce a whole lot of power. It's about 1 kilowatt peak. It's not a huge proportion of the energy use of the house. I think it's maybe 15% now, something like that, but it's a start. And the whole purpose of this retrofit was to reduce demand rather than focus on supply. So quickly moving on, I'll go on to the air source heat pump. So that's the heat pump at the front of the house here that's sitting in front of the extension. It's a 5 kilowatt monoblock heat pump. Monoblock meaning that the entire heat pump is located within a single unit. The refrigerant doesn't leave that unit. So a heat pump works through phase change of a refrigerant, just like a fridge. I could try and explain it, but I'd probably mess it up. I just think of it as amazing magic. in this case, it's using 1 kilowatt 1 kilowatt hour of electricity to produce 4 kilowatt hours of heat. It's 400% efficient, which sounds amazing and impossible, but of course it's drawing in that heat from the outside and putting it into my house. So here is a drawing of the house. Here is the heating circuit. So we have the flow and return from the heat pump, and then a controller in the garage at the cylinder decides whether it should go into the hot water cylinder or direct the heating into the heating of the house, which is, it supplies radiators, goes up and into the first floor directly. And the key thing to think about here is that the heat pump is located very close to the thermal envelope of the house. So if you can see here, there's only a tiny amount of pipe work that's outside the thermal envelope. So the losses associated with that pipe work are a lot less. And that's really important. So those are the pipes there. I mean, they're a bit longer than in my diagram, but they're still pretty short. On the right-hand side of the heat pump at the front, and that supplies the radiators. And the radiators are, well, they're kind of normal sized because they're oversized for a house that's this well insulated with this kind of ventilation system and this kind of airtightness. So they're sized so that the heat pump never has to work higher than 45 degrees C, and that's on the coldest day. On your average day, it's actually operating lower than that. And they're basically normal size, but they are double thin, so they're a bit thicker than they might be otherwise. You can see another one here on the right of this photo. We have some quite nice oversized towel radiators in the shower room and the bathroom, which is always good to make sure that the bathrooms are warm and provide lots of space for towel drying, I think. So they, I think, work really nicely. And here you can see the radiators. So downstairs we've got this 1, 2, 3, and then in the upstairs bedrooms, just below the windows, little radiators there. And as I was saying, it's designed so it works with weather compensation. So that means it detects the temperature of the air outside and provides the lowest possible flow temperature it thinks it can get away with to still keep the house warm, or at least what I've preset it to do, which I think it can get away with. So at the moment, that means it's working at 38 degrees Celsius flow temperature, which is a very low flow temperature. That's when it's fairly warm outside and it gets down. If it gets down to -3 outside, it goes up to 45 degrees C, and that's a lot lower temperature than what you would get out of a gas boiler. And so that's what's key to providing that coefficient of performance I mentioned earlier. At 400% efficient, it's working really nicely, and that's all because we've got that low flow temperature and we've got a simply designed system, really. So it also provides the hot water, as I mentioned. So the controller diverts the heat into the cylinder where it's stored. And this system is slightly different to your average hot water system. So typically you would have the hot water coming out the top of the cylinder, and it would be in a fairly large diameter of pipe, and it would then supply different rooms, and as it approached different appliances, it would branch off and supply your basin and your shower, etc. What that means is you need quite a large diameter of pipe because you've got to share the flow between appliances. So you tend to get people putting in quite large pipes just to be sure that there's not going to be, a trickle coming out. In this case, we've got a slightly different system. So the pipes come out the top of the cylinder, and then they immediately branch down into lots of really small pipes. It's called a radial layout, and it uses micro bore pipe, so 10mm diameter pipes. And then each of those serves the appliances. And so what that means is if you turn on the basin in the bathroom and you let it run warm, it takes a short while to run warm, and then you get nice warm water. You turn off the tap and you've got all that hot water sat in the pipe that then going to cool down. You can't use it in winter. It will potentially reduce the heating bill a bit. In summer, it's just going to contribute to the house overheating. But in this case, because those pipes are small diameter, the amount of water that's left in the pipe is just a lot less. And so it saves energy that way. Again, it's all inside the thermal envelope. So the losses that do occur from that cylinder, etc., are all useful in winter. And this is the cylinder itself in the garage. And so you can see just on the side of this photo, the insulated doors to this plant room. So it's all basically forming part of the thermal envelope of the house. And on the left here, we have nicely insulated pipes coming to and from the heat pump. And that primary circuit to and from the heat pump is just so important to insulate well. Wherever we can, we've tried to avoid the clips bridging the insulation. And you can just see, here's the branching water pipes at the back of the photo here. And so, yeah, that's just a shot to show you the new shower room and the sink where I can get, I think it's hot water with just it's a less than 400 milliliter dead leg is the term for that amount of volume of water that's left in the pipe. And so here's the performance of the heat pump. It has so far performed at 400% efficiency. It's slightly better than that for heating and slightly worse than that for hot water because it's heating the hot water up to a higher temperature. And on average, it's working out at 400% efficiency. That's over the first 6 months, January to June. And so at today's electricity prices, we have basically saved every kilowatt hour of heating that we use. We're saving 18% over what we would pay for gas for an efficient gas boiler. So the heat pump is saving us both cost and carbon. At the bottom, we can see it's saving about every kilowatt hour of heating provided is saving about 74% carbon over gas, and by 2030 that will be I can't see because of the thing, 94%. And so, yeah, I think that cost payback is only going to improve as we see this rebalancing of electricity bills from gas bills, electricity bills getting cheaper compared to gas. And I'll just try and play this video before we finish up. I don't know if you can hear this, but it's trying to show you how loud it is with me clicking in front of it as a sort of reference point. But it's very quiet, slightly louder when it's doing hot water, but I do not know it's on when it's on. I just do not notice it really. And we've started to monitor the house, but as yet we haven't really got enough data to show anything particularly interesting other than it's performing very stably inside, whilst the weather the last week has fluctuated outside. Obviously, we haven't had the heating on yet, but it's performing very nicely and it's very comfortable. So that's the end of my talk. Hopefully I haven't overrun too much. I think we're just about on time and we don't have many time for questions.
Thank you, Olly.
Those are the people I wanted to thank you, but yeah, hopefully there are some questions.
Well, thanks, Fran, and thanks, Olly. That was really interesting. I'm going to go to John first, if that's all right, because we didn't get a chance to get to you before.
Good evening. Great presentation, Olly. Really interesting, loads of detail. I've got a couple of questions, if you don't mind. Firstly, on the floor, it's really tricky doing underfloor insulation like that. Would you do it any differently, given another go?
So in this case, I didn't really have the option of switching to a solid floor ground bearing because of the ground conditions in this area, which made a decision slightly simpler for me. This option using just mineral wool and bits of timber is very low embodied carbon, and switching to like a solid rigid insulation with a concrete screed or something I've calculated would use a fair bit of body carbon. I think it was about 3 tons, maybe a few years of in use operational carbon. So I'm quite happy that I didn't do that, but it is a way to go. It was fiddly, and yeah, it was fiddly, and I trying to think of other ways of doing it, but it's tricky. I think it's a good one to do if you're DIYing it, where you've got, you know, time to do it yourself and you're not really paying someone, because I think materials wise it's quite cheap, but labor wise it's pretty expensive. So that's why I'd say it's a good way to go for DIY installation. But you can do it by going up and over the joist with the membrane, although I think it's probably quite tricky to make it all join up if you do that. So I think it worked all right. I'm not sure how I could have done it better with still retaining a suspended timber floor, but yeah, I'm open to suggestions for my next project.
Well, when you were talking about rolling over the joist, which is what people normally do, you went underneath. Did you? I mean, you get stuck at the kind of the daughter walls, don't you? How do you continuously go underneath the floor joist?
So you do have to wrap it up at the edges, so at the dwarf walls and the edges, and sort of fix it to the sides there. I guess you'd have to do that with the up and over thing as well. In a way, you'd have to stop and start, and you're trying to create something that wants to be a continuous sheet. And you know, if you're wrapping it in 3 dimensions, it's going to become quite tricky, no matter which way you do it. At the end, you have to like feed it under the last joist and then fix it to the wall in some way whilst standing on the joist. It's not easy. Yeah, not easy. But I don't have a better solution for a suspended timber floor at the moment. I think where you've got a bigger floor void, there are options for using a board under there, which would work nicely. Possibly like a wood fibre or a rigid wood fibre board that you could fix up and under. That might be a simpler way of doing it, to be honest. Even in this case, I only had 150mm void left, the bare minimum for building regs, so I had to use a 90-degree drill bit and strips of plywood and screws up into the underside of those battens. So it was certainly fiddly.
Look good though.
Hi, thank you. That's really interesting. I'm much more of a novice than previous questioner, but my question kind of links on. We've got a 60s terrace, and it's built, the whole terrace was built on a concrete raft. So it's like we're sort of almost like the Georgian style of, actually, but anyway, sorry, can't. But so I was going to ask about solid, how you do the floor insulating for solid, if you've got a solid ground floor, if your house is built onto concrete. So it kind of follows on from, because your other question.
Floors, that's a very good question, thanks. It's a tricky one, it's a very tricky one. So there are some really high performance insulations you can put on top of a floor like that to, but you will lose some headroom, as I did here. Because of that plywood, I lost 18mm of headroom at the doorways. Instead of that plywood, I should say, you can just use a membrane, and then you don't lose that 18mm to provide the airtightness. In your case, yeah, you could go for a very high performance insulation there. Those are quite expensive, and you still lose a bit of room, and you know, you can't get that much performance out of a thin sheet of material. So another option is, especially if you're in a terrace and you can get your neighbors to do, well, even if you can't get your neighbors to do it, actually, if you imagine that the ground is a useful thing that insulates from the cold air, what you want to create is a skirt at the front and the back of your building. So you could either a horizontal bit of insulation, i.e. like in front of the building, or you dig down and put like a vertical skirt at the front and back of your house. Then you're basically using the earth as insulation under your house. So whilst you can't get quite the same performance out of that as you would from, you know, insulating the floor, you can definitely improve your house quite a bit. Does that make sense? That's one way of doing it.
And this is cheeky, but related to the terrace question, for those of us without a garage or an outbuilding, if we were in a terrace and a whole terrace wants to upgrade, it might be easier, but I don't know. But as individual houses tends to be how we look at our homes in the UK. What's it called? The cylinder and the pump, you know, the plant material sort of takes up quite a lot of room. What would you advise? How is it? Does it mean that you have to put an outbuilding at the back, or how do people manage in a sort of, you know, Cambridge is full of terrace houses, so
Yeah, that's a tricky one.
thank you.
Good question again. Like, I would say that my plant room is very generous. Like, there's lots of space left over in it, and you don't need as much as what I had there. So there are new products coming onto the market. I think there are things like heat batteries, or we're using phase change materials, so you can store heat in a smaller object than a big tank of water. So you could look into those sorts of solutions, and they are even looking towards producing ones that would fit inside a typical kitchen cupboard, like the upper part of a kitchen cupboard, although I don't think those size are yet on the market. So other than that, you know, you do have to just find space for a cylinder when you use a heat pump, unfortunately. If you're doing it as a single heat pump for your own house, I suppose, yeah, you were sort of hinting at an idea of getting all your neighbors together and doing something more collectively, which sounds like a great idea to me. But yeah,
Can I jump in, Ollie? Because actually we've got there's a few houses, a few homes that have got air source heat pumps that have been doing tours this season, and all their case studies are on a website, and you know, there's terraces on there who haven't done the extension, and I'll put it in the garage, so it might be worth having a look at how they've managed it. I've seen people put them in some rather fancy cupboards that they've built in the spare bedroom and all sorts of things. So it's worth having a look at that. And there's also a talk next Monday on low carbon heating options, which includes heat pumps, and it might be a good place to raise that sort of question and discuss that there as well.
Thank you.
Yeah, and the roof insulation, it's in eaves, fulfilling the joist, and I guess a membrane on top of that. Were building control okay with that? I'm doing a similar project at the minute, and building control are insisting on, you know, 50 mil breather gap up across the top of the roof. So I guess is it called a hybrid roof, Ollie, where you fulfill the joists?
So well, in this case, all the insulation is above the ceiling joist because we've got that green deck that's producing the airtight there below the insulation, and then it's just sat there on top. But yes, I understand the premise of your question. So yeah, it's an interesting one. So I'll try and explain for people that might not understand the context here. My roof was re-roofed, so I was putting in a new breather membrane under the slates. So what that allowed me to do was to put in a batten, it's called a counter batten, that runs vertically on the roof, and then you put the slating battens running horizontally, and you have a ventilated void above that breather membrane. And so that means that if any condensation forms in that cold loft against that membrane, it should diffuse through and then get taken out via that void under the slates. And I used a particular breather membrane that has what's called a BBA certificate for that particular use. If you look at the building regs, and if you look at British standards, there's a recommendation that you might want to ventilate a roof like that, and especially you need to if you've got a non-permeable membrane under the roof. So in an existing situation where you're not re-roofing, you're not providing new slates, and you've got a non-breathable membrane underneath, then there's a suggestion that you should ventilate under it. And this is probably where your question sort of comes from, I'm imagining. Is that right? Is that the case in your case?
Yes, exactly. Yeah.
Yeah. So yeah, I got around that by virtue of the fact that I was re-roofing at the same time. It is more tricky if you're not, in which case you do tend to need to provide this 50 mil gap that you mentioned. And ventilate it, and then you just want to be really careful about ensuring that that ventilation doesn't interfere with the performance of your insulation. And so that basically means ensuring that there's no leakage path around the insulation, which can be the case when you're using like rigid insulations, because it's very hard to cut those rigid insulations tight between ceiling roof rafters and things like that. But you can use membranes and things to try and separate out that ventilation from your insulation. But it's a tricky one again, and it's a good question. Tough
Thank
questions.
Good answer.
I've just posted a link. There is a building control service that works for the local authority. There's a link to them that might be useful in terms of getting in touch and getting some advice as well. They're quite willing to just help advise when there are some of these issues. So thank you very much. Well, I think we'll wrap up. I'm just going to share this again quickly. So thank you for coming. It's been a really interesting talk. Thank you, Olly. As I say, the recording will be online. It'll be sent to you along with the slides and all the links in the chat and so on. We are a charity, Cambridge Carbon Footprint, and if you would like to support us, please feel free to go to our website and donate, come to any other events. Okay, we'd be very grateful. Next steps for you to get started on your retrofit, I've put some links up, places that are really good to go and get some advice, help you get started. We've got some things on our website to help you get started. There's a few more tours and talks going on this weekend and over the next few weeks, so please do check out what's on there. There's also lots of past case studies available on our website. We've also got a human library event coming up on the 21st of October at the Grafton Centre, which is an opportunity for you to sort of book and speak to an expert kind of one-to-one about your own questions. That's a really useful resource. We're starting our thermal imaging camera season soon, which includes 4 training sessions between November and February, and a scheme where you can borrow a thermal camera, which I think Olly did in his house to begin with, as one of the ways he found out what was needed doing. It's a really useful way to find out where's best to start on your home. And of course, you can use the Transition Cambridge tool on their website as well. So thank you very much, everybody, for attending. Thank you very much for allowing us to go for 10 minutes. I hope you all have a wonderful evening. Okay, go enjoy some Bake Off. Okay, take care and thank you very much.
Thanks, Fran. Thanks, Olly.
Thank you.
Thanks, guys. That was really good.
Cheers, thanks.